and it would be good to learn how to actually sort of visualize networks and actually also talk a little bit more about, you know, the network structure. So how you can actually learn, look at the networks and tell more about the networks. To get started, I'm going to talk about K-core decomposition, and this is actually a very, very powerful technique that allows you to sort of disassemble network into layers. And in fact, it's a very, very good pre-processing technique for visualization. We then will talk a little bit about this notion of mixing in networks. It's sort of the way and why and how nodes with different degrees connect to each other. And then we'll spend the rest of the lecture discussing different network visualization techniques. So we have seen this picture last time on the last lecture. I actually finished up last lecture with this picture. And last time we talked about various network communities. And we looked at the algorithm that allows you to find those communities. And in fact, you know, like if we look at this picture, say here is a community, and there is another community, and you know there is another community, and so we know algorithm that allows us to detect those communities. What we are interested now is actually in finding and detecting the core of the graph. So that part of the graph that is, well, mostly densely connected, and this is a part of the graph that usually represent like sort of, you know, geometric center, and very often it is actually even logical center for the graph, in the sense that it may be the graph has been if it's graph evolving with time, graph started there, or if it is graph describing some sort of you know, again, maps or anything else is going to give you the center of the graph. So in here, you know, core is right there, and we want to be able to extract it. Now, of course, we can actually use the same type of techniques as we did where we looked for communities. You can think, okay, well, you know, if we cut out these guys, what remains is a core, which is sort of true, except for what we would like to be able to do is to sort of take the core and like peel out layers and have this, like, I mean, almost like matryoshka like representation of the graph, right? So when you have like different layers built on top of each other, going from like very, very tightly connected centroids of the graph. And that's what K-core algorithm will actually help us to do. So what's K-core? Well, there is actually a formal definition. You know, the definition we're going to use today is a constructive definition, right? So it actually defines things by construction. And the idea is the following. So if we take a graph, and this is a picture of a graph, and recursively delete all vertices and lines incident with them, so we delete all the vertices of degree less than k, the remaining graph will be called a K-core graph. So let's look at this example and just sort of try to follow me. Let's say we're gonna look at this graph right now. It's connected graph, and so every vertex in this graph has a degree 1 or more. Okay. So let's pick up k equal to 2 and see, like in a constructive fashion, what should be done to get this k equal to 2 core, or it's called 2 core, or you know, k equal to 2 core. So to get this k equal to 2 core, we need to delete all the vertices of a degree less than k. So all the vertices of the degree less than 2, which is, you know, what vertices have degree less than 2? Well, the degree of the vertex is 1. So delete all the vertices of the degree 1 and do it recursively. So what does it mean? Okay, let's take a look right now at this picture. There is a vertex of degree 1 right here, right? We're obviously deleting this vertex. There's a vertex of degree 1 is here, deleting, 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 deleting. So we went through once and deleted all the vertices of degree 1. But now what happened is there are other vertices whose degree now dropped from maybe 2 or 3 to 1. Let's take a look at this guy. So original degree of this vertex was 3, but now after we removed 2 of its neighbors, it became 1. Or if you look at this guy, the original degree was 2, but when we removed one of its neighbors, since its neighbor has a degree 1, the degree of this vertex dropped to 1. So again, what the key to finding this k-core is the word recursively. So we went once around and deleted all the vertices that had degree 1. Now we need to go again and pick up sort of what's left if there are other vertices that left with degree 1. And so this is going to be this guy. So this guy now has degree 1, and this guy now has degree 1, and this has degree 1. So now we deleted recursively all the vertices that had degree less than 2. Well, in this case, it was degree 1. And so what's left is called the core equal to 2, or 2 core of the graph. So what's left is this, and it's called 2 core. Now, if I want to find core k equal 3, or 3 core of the graph, what I'll need to do is I'll need to do exactly the same procedure, and then I will end up with that central part. And this particular graph does not have core higher than 3. So the important thing to note is that every vertex in k-core has a degree greater or equal to the number of the core, right? And the cores are so that they're arranged one over another, right? They're sort of layered. Now, there is another definition that we need to understand, and that's like slight difference. There is a k-core and there is a k-shell. So k-core, in our case, this is a central core, right? So this is core equal to 3. This is a core equal to 2, this entire thing, right? This is a core equal to 1, all the nodes. When people talking about shells, they actually mean shell. So this is a shell equal to 1, which means then all the nodes that belong to it belongs to the core equal to 1, but do not belong to the core equal to 2. This is a shell. So this is a shell right now of degree 2, where all the nodes belong to the core 2, but do not belong to the core 3, and so on. Okay. So this procedure, this recursive procedure, allows us to build either cores or shells. But in any case, however you use it, the point is it allows you to create this sort of representation of the graph, where you can go from like the very central point, very central part, to the layer on top of it, to the layer on top of it. Okay, so it sort of gives you this layered representation of the graph, and quite often, you could be very interested actually in this very central part because it tells you a lot about the graph. So this is a very, very powerful technique. It's actually computationally not very expensive, and so it's almost linear, and so you can actually do it on very, very many graphs. And I strongly recommend it as a pre-processing step when you're analyzing networks, and especially if you try to visualize a network, because quite often you'll have a lot of nodes of low degree nodes, and this technique allows you to actually get rid of them in a very consistent manner. To just give you an example, let's take a look at this Dockery Karate Club graph. We've seen it many, many times. I can run k-core algorithm on it, and what we're going to see is there is a central 4 core, which is this one, right? It is all the nodes in that core has a degree 4 or above, and they're connected to all the nodes within the core with that degree. Then there is a next layer, which is a 3 core. It is this including green guys. Then the next layer, it's including yellow guys. And then there's a final sort of the 1 core per node is only the node number 12. It has degree 1. It's only one in this picture with degree 1. And so these are cores, and what sort of lays in between are shells. So in fact, the green, I'm sorry, the blue one is, well, it's 4 core and 4 shell. It's the same story. Now, green color is 3 shell. Yellow color is a 2 shell. And well, and the red is 1 shell, right? So again, shells is like, it's really shells, right? And cores is their entire graph that we see here. Here's another example. This is a much larger graph. This is a much larger graph, and I'm also trying to build this sort of core representation of this graph, and it's color-coded based to the core representation. And for example, core of degree 1, it's pretty much all the graph in there, right? And then core degree 2 is less nodes, 3 less nodes, 4 less nodes, etc. So this is a picture of core 1, and by whatever reason I cannot write. Okay, this is a core 1. This is a core degree 2. This is a core 3. This is a core 4, and it actually consists of 2 parts. And this is a core 5, core of degree 5. So every node in this in here has at least 5 neighbors. So the point is, notice how original graph had, like, for example, long chains. And if I, for example, wanted to just remove the nodes of degree 1, I wouldn't be able to get rid of this entire chain. I would just, cut one node, one node from here, and we'll still have the chain in place. But it's only because we're doing this in recursive fashion. The 2 core already does not have any of those sort of chain structures, right? And 3 core, it does not have any nodes with degree 2 or less. So this is a way to sort of disassemble the graph and look at it. And the colors here, they correspond to the shells we extracted, and so you can see where they came from the original graph. Now, the way it's laid out, of course, is because of the way we draw graphs with the sort of force-directed layouts. We're going to talk about them. Those layouts, in fact, force a lot of nodes that are central to become in the center of the picture, the center of the graph, and then sort of those that are connected loosely to them, they will be sort of built around it. Any questions about the core structure?
No.
Okay, and of course there is the good news is there is a command in iGraph which is called coreness, and it actually it generates for every node its core value, and so you can take that value and create cores by aggregating all the nodes with appropriate core values, right? So it's iGraph actually. Okay, let's move on. So the second topic, which is not connected to cores at all, but it's also about understanding of the graph structure, and it's actually quite important, quite important topic, and it's important to understand it. So the idea, it's called the mixing pattern of the graph. So the idea is the following. Quite often, one of the things you notice about the graphs is how nodes in the graph are connected. And if nodes that are similar are actually connected in the graph, or maybe they're not, right? So what I'm trying to say, by looking at the graph, you might notice that, say, for example, low degree nodes connected only to low degree nodes. Or you might see that, and high degree nodes connected to only high degree nodes. Or you might see the situation where low degree nodes connected always with high degree nodes. So this situation actually described by this notion of mixing. Another example, more of like social example, yeah, if you have friendships, do people of the same income are friends, or you more often see like rich people being friends with poor people? Well, I mean, answer to that question. So within the social network analysis, we define two types of mixing patterns. And so one is called assortative mixing. And assortative mixing means like links with like, right? So when you look at the two nodes, if their attributes are similar, then there is a high chance that they're connected than not, okay? And this assortative mixing means like links with dislike. Attributes of connected nodes tend to be less similar than if there were no such edges. And by attributes, we mean like, age, sex, geography, and sort of vertex degrees. So again, the story of, like in high school friendship, would boys most likely to be friends with boys, or boys with girls, right? Or boys among themselves, girls among themselves. The notion of mixing in among people with different ages, right? If people of the same age are more often connect in social networks, or people of different ages connect. So of course, in social network, it's more of assortative mixing. So it's of course people of the sort of same age in terms of, it's assortative mixing in terms of age, right? But it quite often becomes a disassortative mixing in terms of like, say, gender, right, or sex. So that's a general idea. Here's an example of very much assortative mixing. This is a visualization of a Twitter network, and every node is their user, and the edges are retweets, and the color coding is red color is red leaning and users, and blue color are left leaning. So in US it's Democrats and Republicans, and the point here is that of course Democratic journalists and Democratic users will of course retweet tweets from Democratic guys, right? And so you get strong blue color where blues retweet blues, and of course red stays within usually stays within red, and there is of course some boundary, and there is some connectivity there, but it's very, very much political polarized, and that is example of assortative mixing. And now there is another term for this, is called homophily. Again, the idea it means similar connects to similar. Okay, so in this case, in this picture case, we're talking about the property of the node, and in this case, it's political preference, right? So it's assortative mixing with respect to political preference. And in plain English, that means people of the same political preference connect to each other with higher probability than people with different political preferences. Okay. All right, so here is another actually entertaining example. This is quite famous paper by Harvard scientists Christakis and Fowler, where they actually monitored the spread of obesity among people for like 32 years. And what they found is shown in this social network. So the node coloring is yellow nodes are people who are obese, and they define obese as a ratio of, as actually body mass index greater than 30. And green nodes are those that are not. And there are different type of ages. There's relationship, like purple denotes friendship, and orange family ties. And you, for example, can notice how like obesity actually propagates in families a lot. And so yellow nodes quite often connected to other yellow nodes through, for example, orange or family ties. And that means, there is associative mixing with respect to, the obesity problem. So how can we actually measure this, right? I mean, we can look at the network, we can look at the colors, but of course there is a way to give like a numerical value. And there are several numerical values we can talk about. Well, if we have a mixing by a categorical attribute, and categorical attribute means, again, color, gender, ethnicity, political preferences, then the way to measure it is through what's called assortativity coefficient. And it's really, I'm not going to go into details of why it is and sort of why it is the way it is, but it is very, very much look like the modularity coefficient, the modularity coefficient that we looked at last lecture, looking at network communities. And so the idea here is very simple. This delta symbol means that it's actually equal to 1 if both values of two nodes, node I and j, if both of them belong to the same type, right? If they're the same type, say same political preference, then this, Kronecker symbol delta is equal to 1. And if they're not, it's equal to 0. And then what this is the difference in between the actual connection among those people minus this product is the connectivity pattern that you would expect if the network was random. And so what this says is sort of what's excess connectivity among people compared to random network if the people are of the same sort of preference or of the same type. And that then we just sort of add those values up and normalize them. And so what this says is if people of the same preferences are more often connected than at random, well, then we definitely see associative mixing. And if they're less, then we will see disassociative, and so this coefficient will reflect it. So we can actually measure it. Now, it's called, within RE graph, it's assortativity. That's sort of the command you can look. You can just give one command and you'll see whether your network, based on the type of nodes you use, whether it's assortative or disassortative. And if you have actually scalar values, so for example, you have age or income, then it is very similar formula, except for instead of just delta function, Kronecker symbol, we're actually putting the actual values that nodes carry. And so what this is really traditional correlation function, but where you calculate correlation not among all the nodes in the graph, but only among those that are connected. And it's also sort of comparing it, the correlation you have, to the correlation that the graph would have if the connections were random. And that's what's called, that's sort of assortativity when you have a scalar values, right? So there is also one more important type is, special type is this assortativity by node degree. So the idea is that instead of just looking at age or weight or zip code for the person, we actually, for the type of the values to consider, we actually look at node degrees. And here we're literally talking about the fact that whether in the graph nodes of high degree connected to the nodes of low degree or other way around. So if we have a node with, say, a low degree node, if we have this kind of situation in the graph that occurs most of the time, or do we have, say, this kind of situation? when high degree node is connected to low degree node. And there is also a special command within iGraph. It's assortativity by degree. And so why is this important? Well, that actually tells us a lot about the graph structure. And on the next slide, I'm going to show you a few examples of that. So here are the three graphs, and actually it's a very interesting picture. I borrowed it from the upcoming book by Barabashi. So here are three examples of three networks. And so far we talked about assortative network, right, and disassortative. So if you notice, let's look at the assortative network. Let's look right here. If you notice in this network, the way nodes are shown, nodes, the size of the node and the color of the node are proportional to the node degree. And low degree nodes are purple color, medium degree nodes are green color, and high degree nodes this yellowish brown color. So if you notice in this graph, nodes of high degrees are connected with nodes of high degrees. And nodes of low degrees are connected a lot to the nodes with low degrees. So what we see here is the matrix that describes the connectivity, the type of connectivities we have. So on the axis here, we have node degrees, the values of the node degrees, and the intensity of the color just corresponds on the connections, of how many connections in between those type of node degrees we have. And if you notice, the connections among low degrees nodes, and here is like 5 or whatever, and there is some intensity in there. And there is also a lot of intensity. There is intensity in here where the connectivity patterns, it's a high degree nodes connecting to high degree nodes. But what we don't see anything here, because this area would correspond to low degree nodes connecting to high degree nodes. And it's missing that. And so that means this is assortative mixing. If we look at this graph, what we notice is that the nodes of a high degree, like right here, are very well connected with the nodes of low degrees. And so what we see, on this matrix, a correlation matrix, you can call it correlation matrix, that when you have high degree connectivity with low degree nodes, it's again at this corner. There is a lot of intensity, which means there is a lot of connections like that, or sort of other way around, a lot of connections like that. But those corners are empty because there is no connection of high degree nodes to low degree node. I'm sorry, high degree node to high degree nodes right here, and there is no connection of low degrees node to low degrees node right there. Okay, so that's disassortative mixing. And if you can also have some sort of neutral mixing where there is no preference whether it's assortative or disassortative. Then the matrix will be connectivity matrix, will correlation matrix will be very uniform and smooth here. So that's kind of the idea, the visualization of this idea. And if we try to look at some graphs that I built like very explicitly for assortative or disassortative networks. So if the network is assortative, again, you have high degree nodes connected to high degree nodes, and low degree nodes will be connected to low degree nodes. And so as a result, you will see something like very densely connected centroid of the graph, and then you will have a lot of coming out like edges, long edges, like long chains of edges of nodes. And that's a signature of assortative mixing. Now, when you have a disassortative mixing, which means low degrees connected to high degrees, you will very often see this kind of fan-out structures, right? Where you'll have high degree nodes and lots of low degree nodes connected to that high degree node. So that's a signature for the disassortative network. So you can actually, by looking at the network, you can actually say whether it's assortative or disassortative. But what's true is also other way around. By computing the number and without seeing the network, and the reason you don't see the network because it can be very large, you can actually sort of predict that if you have a assortative network, you most likely will have a lot of like longer chains in the network versus disassortative network that will have this sort of fanning out structures. All right. Any questions about this assortativity, disassortativity story? All right, let's move on then. So the next part, okay. All right, so the next part of the lecture is really about visualization. It's actually also a pretty big subject on its own, but it's also very practical because, you know, in many cases when you work with networks, if they're small, you really want to see them. And, you know, when you present your work, your results to other people, I mean, you know, one picture goes very far compared to just sort of, you know, words description. So typically when you want to show a network, what are you given are nodes, right? And edges. So you have nodes and the connection among nodes. What you're not given are coordinates of those nodes. Like you don't have X and Y values where to place the nodes in a picture. Or maybe sometimes it's X, Y, Z values. And so big part of network visualization story is really about computing those X, Y representations for nodes. Now, there are sort of other things you could do, right? You can, for example, when you position different nodes at different spots, right? Then you have to connect them with edges. You can connect them with straight edges, or you might want to connect them maybe sometimes not with straight edges, but with, say, you know, curving edges, depending on the visualization you want to build. You can also then look at the color and the size of the nodes, and you can control them. You can look and check the color and the thickness of the lines that connecting them or edges. And when you do this sort of graph layout, there are other things you might think about, like, for example, if you would like edges not, so you would like a layout where you minimize the crossing of edges, right? You don't want edges to intersect. In very many cases, it's impossible, but there are some types of graphs, like planar graphs, where, you know, you can actually draw the graph on the plane without the intersection. So, but again, the main problem, you know, is defining X and Y coordinates for the nodes. As always, there are a lot of algorithms that allows you to do that. Some of them works better than others. So we're going to look at a few examples right now. So first of all, when you don't know what to do and you got a graph, you know, some graphs are actually pretty hard to draw, and computing those X and Ys is called creating a layout. Okay, so you might want to start with like simplest graph layouts to just, you know, take a look at your data. And the simplest one, of course, will be like circular layout, where all the nodes just positioned around the circle. It could be a grid layout where all the nodes positioned are just on a grid, or it can be maybe a random layout where each and every node just given random XY coordinates, and then you draw the picture. Now, why would you want to do that? Well, simply because they're very, very cheap to compute, very fast, and so, you know, it can be like very, very easy first step. So, you know, trying one of those layouts, and they all have, by the way, they all exist in iGraph. So the second sort of layer of defense, right? Second type of layouts you might want to look at are so-called force-based layouts. And the idea here is the following. You might think of the graph as a bunch of masses, you know, like little balls connected by springs. And each of those balls has a certain mass, and then, you know, your Hooke's law and physics comes in, And what you're trying to do, you might actually also think about those guys to carry certain charge, for example, electric charge, and then they will be repelled, but the springs will try to keep them, not keep them from flying away. Like sort of this kind of notion of forces and interplay of forces will create particular structure, will create, I'm sorry, particular layout for a graph. And spring-based is literally based on this model of springs. There are more advanced algorithms and layouts that are optimizing, a little bit of a different function, but still trying to like come from this physics-based world. And so, if you look at the spring layout, it's probably not the best layout, but probably one of the most popular layout is this Kamada-Kawai layout, or there is this Fruchtenberg-Reingold. They're similar in some sense. They're both optimization functions, and they create the pictures of the graph I have shown you previously. So if we want to dig a little deeper, that's sort of the explanation of force-directed layout, right? So what you think about the graph at the nodes as connected by springs, and sort of one of the ideas is you give some sort of initial positioning for those nodes, and then you let it go and let sort of and just literally model how springs will move nodes around until it gets to a sort of stable position. And the Kamada-Kawai model, it actually works on a stress minimization. The idea there is you actually optimizing, difference among the coordinates minus some sort of optimal distance, where it says, okay, well, the energy will be minimum if on average distance among nodes is this equal to Dij. And Dij can be just a constant given by you. And so that computes this value of the stress, and the locations are being optimized through this value. And this is your adjacency matrix, the connectivity matrix. So the good news, again, you don't have to write the code yourself. You can just use, prepackaged solutions, but some of them require parameters. And for example, some parameters could be the stiffness of the algorithm. Well, the stiffness, that refers to the stiffness of the springs that used in this modeling. Another example, a little bit more advanced. There are various types of actually, taking the graph, thinking about the graph as a matrix, the adjacency matrix, and then running various types of analysis on the matrix, trying to convert that into coordinates. Like one of the examples will be taking the matrix and doing principal component analysis or singular value decomposition on the matrix. And then what you do is you calculate principal component analysis, right? You decompose your matrix into the eigenvalues and eigenvectors. You solve something, let's say if the matrix is symmetric, you will solve something as AX equal lambda X, which gives you eigenvalues, and will create for you like a lot of eigenvalues and eigenvectors. And then you take two top eigenvectors, x1 and x2, and that's sort of what's used as a projection. So use values given to you in those eigenvectors as coordinates in this two-dimensional space. And MDS is just a different, well, another approach. It's called multidimensional scaling, but the idea is the same, that you're trying to find some sort of subspace projection of your matrix. And so if I calculate coordinates using those methods, then we can put back our nodes. Well, we place the nodes where the coordinates are, and we connect them by the edges, and you will see those two layouts. Now it's called SVD layout and it's called MDS layout. I would say sometimes they work really well, sometimes they do not. Not the method of choice, though I do, of course, once in a while look at the PCA decomposition, well, because of many other reasons. But overall, you can use them too. Any questions so far? Okay, good. So I also want to briefly touch upon a very, very important and practical way of visualizing graphs is through actually drawing the adjacency matrix. The reason why it's important is because quite often, especially when you have large graphs, large networks, it's almost impossible to see them and to do a good job visualizing them. One of the biggest reasons is just because you have visual clutter, right? If you have like a graph of size of even 1,000 nodes, it's 1,000 points on the screen, right? And most of the screens has a resolution of like several thousand by several thousand. So just by drawing nodes and having a node being 1 pixel wide, you already can take like the entire screen size. And so not a good idea. So that's why it's very good to look at the graph and try to learn how to how a graph can be represented by sparse matrix visualization. So sparse matrix visualization is very simple. So what it is we take the adjacency matrix, right, that corresponds to your graph, and the adjacency matrix will have, will have bunch ones and zeros, and those ones corresponds to the connections, right? And so, for example, I take this as the first row and 1, 2, 3, 4, fourth column. What I'm saying is that the node number 1 is actually connected to the node number 2, right? And when there is no connection, well, it's 0 in this matrix. So when I have a sparse representation, zeros are not stored. It's only ones that are stored, all right, and empty spaces instead of zeros. And then sparse matrix visualization is just saying, okay, well, instead of writing ones, I'll just put there a black box, okay, or dot. And so that's how it gives you structure. So what we see here on the axis are just nodes that are ordered by their number, 1, 2, 3, 4, 5, 6, 7, etc. 1, 2, 3, 4, 5, 6, 7. And the way we read it is node number 1, for example, connected to node number 6, right? And that's sort of the picture. Now, it might not make a lot of sense for a very small graph, but it definitely makes a lot of sense when you have large graphs and matrices. So here, I'll give you a sort of example of a little bit bigger graph and the matrix on the left side. Now, by looking at this matrix, you sort of realize that, well, yeah, there are a lot of connections, but it looks quite random, right? So you don't see a lot of stuff from the matrix, right? It's a graph picture that gives you much more. So the question is it possible to do some sort of operation on this matrix, like, for example, change rows and columns, change, just sort of permute it, so that we will see any structure in there? And the answer, yes, you can. And there are several algorithms of doing so. Now, one algorithm is also very efficient and very simple. It's called well, minimum degree ordering. There are actually two of those. There's a minimum degree ordering algorithm, and there is what's called Hill-McKee ordering. So the idea is the algorithm tries to change rows and columns such a way that overall the matrix will look like a narrow band along the diagonal. So what's the point of this exercise? Look, what we're trying to do is we're trying to find, take a particular node, right, and a corresponding row, and try to, put it into a different position in the matrix such a way that we'll see certain type of structure. It also corresponds to just renumbering the nodes in the graph. And so imagine that you can renumber the nodes in the graph such a way that those nodes that are connected will get consecutive numbers. So if you can do it, then in the matrix format, you will see little blocks. I'll try to show you on the next slide a little bit more detailed explanation. But the point here on this slide is that by running some very simple algorithm, you actually can get this picture on the right, where you do see blocks, and blocks means those group of nodes that are tightly connected among themselves. And so you realize, by looking at this, you realize that the matrix structure is not entirely random. It's not a random graph. It's not random connections. There is some structure in those connections. So how do we read this? This is a great picture I borrowed from one of the recent papers that shows you, that maps for you, the graph representation and the matrix representation. Like, so what things look like in the matrix world and what they look in the corresponding graph world. So notice, like right here, we got a cluster, for example, right? There is a cluster here. And in terms of the graph, and I'm sorry, in terms of sparse matrix representation, it will look like a group of nodes connected to each other. Now, if we have another cluster next to it, and even overlapping, well, those blocks will overlap a little bit. Now, red clusters, they're actually cliques, which means every node is connected to every other node within that group. And so you will see here a very, very densely connected, completely populated block. For traditional clusters, like purple one here, it's not every node connected to every node, so it will still look like a block, but with some empty spaces. And if you have a very particular type of connection, like biclique, it's called biclique, it means there are a group of nodes on one side and a group of nodes on another side, and there is a sort of connection only between these two groups. There is no within the group connection. You will start seeing this type of picture, in the matrix. So that means, if you kind of understand this mapping, it's quite often enough for you to look just at the sparse matrix representation to actually understand what the graph would look like. And again, for small, the power of sparse matrix representation is that to draw a graph, you actually need to go through graph layout algorithm and hope that layout will nicely lay out things for you, and so you'll be able to detect by your eye, groups of nodes. While in the matrix world, you don't need layout algorithm, but what you need is this sort of ordering algorithm. And please notice how things work here. Now, the reason we're seeing this cluster is because the way the numbering is done, it is consecutive numbers, consecutive node numbers, node 5, node 6, node 7, node 8, node 9, right? This is the nodes are numbered consecutively within the cluster. And that's why we're going to see it here as a block. Now, if they were numbered randomly, we'll never see that block. So then the question becomes is, when you have a graph, how do you renumber nodes such a way that the nodes that are within the same cluster actually gets consecutive numbers? And well, there's no actually easy way to do it, but we can use algorithms like similar to those we looked at last time, where we looked for the communities. And so, for example, you can run this community detection algorithms and try to build the communities and then number according to the communities. Or you can use actual sort of clustering, very, very straightforward clustering algorithm to also get this type of numbering. So here is an example for the particular graph you saw, where I just took and ran sort of traditional hierarchical clustering on that algorithm. And so, it's hard to see, but right here, we get node numbers, and nodes are shown here such a way that nodes belong to the same cluster. Well, they're next to each other here. And so, for example, in this case, the traditional clustering algorithm found out, like, there is one cluster here, there's another big cluster, third cluster, fourth, fifth, sixth cluster. We could have discovered them by community detection algorithms. So then what I can do is I can actually try to read numbering like along those clusters layout, and renumber my nodes such a way that nodes belonging to the same cluster will have consecutive numbering. And that's sort of one of the ways of doing it. Again, the good news, you really don't need to write any code to do that. There is, you can create clusters. You can do this dendrogram plot that gives you this picture, and it will also give you a readout of the node numbers that are consecutive for this to have this layout. And then you can just take that permutation and use it to permute the matrix. And here is an example. This is actually the picture we have seen. Let me go back for a sec. Okay, it doesn't want to go back. So this is a picture. This is the graph we have seen before. What I have done here is I renumbered the nodes according to the color coding you've seen on the previous slide, right? So we see here those groups of nodes, and then the matrix has been permuted based on the same. Based on that numbering. So it's in fact this matrix, right? This matrix that with the random numbering wouldn't show any results, wouldn't show us anything. It's we did this very simple ordering for it. We kind of understood that there is some structure, but the structure was not very clear. But when we ran the algorithm for this clustering algorithm, and then renumbered nodes based on those clustering algorithms, that matrix start looking like this. And of course, you can look at the corresponding graph, but since now we know how to read the matrix, we understand that, well, there is a very strong cluster here, there is a weaker cluster, there is another cluster, and there is a sort of bigger cluster, and there is sort of embedded another cluster into it. So it allows us to discover clusters and see them in the matrix form. So I would actually, like, from the practical perspective, I would strongly recommend using various sparse matrix type of visualization to actually look at the graph structure. It just works. Any questions about that? Okay. Oh, and I forgot that there is another slide here. So this is another example actually from some pretty bigger data. I think it's like around 10,000 data points here. You also, if you look at the sort of original picture, the way the data was given, it looks like that, the matrix. But then if you find the correct permutation, and this was done with one of the algorithms that's called Spectral, bipartite graph partitioning, then the only thing which was done is like permuted rows and permuted columns. Based on that algorithm, we start seeing structure. And again, now we understand that there's a lot of clustering, and some of those actually clusters have like even hierarchical structure, like in here, right? Or like in here, there's big cluster and there's like smaller clusters embedded into it. Okay. So a few words about tools just to make it practical. Now, for small networks, you can easily use just R itself, simply because, well, it's easier, and R can actually handle small graphs. But when you get to larger graphs, life is becoming harder. Here's a bunch of tools that are available. I personally use most of the time Gaffey. It has probably the best layout algorithms and the best sort of coloring options. So I do use Gaffey a lot, and sometimes I use YED. It's another program that allows you to create pretty visualizations. Here's an example from YED, and the site is YWorks. It's this type of graph. By the way, by looking at this picture, can you tell me if this is assortative or disassortative network?
Assortative.
Or disassortative?
Disassociative.
It's disassociative, right? Because there is you can see this sort of spreading a lot of low degree nodes connected to high degree nodes, right? It's sort of the signature. You see this things, right?
Without chains.
Yep. And this is an example from Gaffey visualization, which actually like literally allows you to create very pretty pictures, and you know, do a lot of sort of color coding, the thickness of the edges, different fonts, different backgrounds. That's another example of Getty, where you have, again, nodes are proportional to node degrees, and it's also color coded, etc. So that's sort of probably my favorite tool for right now to use. And also, if you're I'm sorry.
Was question.
Yes. Okay. And just another sort of reference point, if you're interested in all kind of this type of graphs and various visualization techniques, there is a terrific website. It's called Visual Complexity, where they collected from around the world lots of graphs and lots of visualizations, and you can pick up really cool ideas from there. And then the best part of this website is that they actually reference the original data and reference the places they collected graphs from, so you can actually even learn on how those graphs were created. So, you know, if you're into this, strongly recommend you checking it out. And there's, as always, there are some references here on the algorithm we talked about today. And that is it. Do we have questions? No questions? Okay. Andrej, please take over if you're there.
Okay.
All right. Thank you, guys. And I'll see you in a couple of weeks.
Goodbye. Thank you. Bye-bye.